My name is Seung-Yeon Son. I'm working in NOAA Nested Star, Maryland, in USA, since 2007, February 1st. It's quite long. And as a Tom mentioned, I'm originally from South Korea. I came to USA in 1999, and I was working a little bit in the Bedford Institute of Oceanography in Canada with the Trevor and Shubha attendants and some other colleagues here. Okay, my talk today is more about remote sensing in coastal and inland waters, focusing ocean color remote sensing. So I think you already had the lectures in previous 4 lectures. Those covered more introductory information about ocean color remote sensing. So I'm not going to dive in. I'm going into some information about ocean color remote sensing, but try to show more research results from my previous study. Okay, before we're going to the coastal inland ocean color remote sensing, I'd like to share with information about the satellite ocean color sensors. Some of you are already familiar with these sensors. There are historical satellite ocean color sensors. I think the most important sensor is the CGCS. It's Coastal Zone Color Scanner from NASA. It's on board Nimbus 7, which is the first ocean color sensor operated from 1978 to 1986. And the next important thing, in my opinion, is the CWIPS. That is more practical. The first ocean color sensor launched by NASA and is operated for more than 10 years, from 1997 to 2011. CWIPS data provided a lot of good research products using ocean color data. And there are some other sensors by Japan, OCTS, and GRI, and the MED is also important satellite sensor by European Space Agency. And then the last one is GOSHI 1. I think that is quite important sensor in ocean color community, which is the first geostationary ocean color sensor by Korea, which is successfully operated for about 10 years, 2011 to 2021. Here's an example of a coastal zone color scanner. The first ocean color sensor from 1978 to 1986 on Nimbus 7. The bottoms are the example images of from CGCS. Here's current satellite ocean color sensors. There might be some update, but the GOSHI 2, the geostationary ocean color satellite, is GOSHI 2 replaced GOSHI 1, which is launched in 2020. And another important sensor is MODIS Aqua by NASA, which is launched in 2002, which is still operating over 20 years. But as I know, MODIS Aqua is retiring this year because of the quality issues. I think it's sense degradation issues. And there are many ocean color sensors by European Space Agency, Sentinel series, Sentinel 2A, 2B, 3A, 3B. And there's a BEARS sensor by NOAA, which is launched in 2011. BEARS on SNPP, That's operating for about 10 years with the Modis Aqua, so we can transit smoothly. And there are two more Beers series by NOAA. Beers on NOAA 20. Actually, there is a JPSS, J1 sensor, we call. And last year, October or November, the Beers on NOAA 21, the J2, is launched. So now we can go to the satellite ocean color application algorithms and its applications in the coastal inland waters. As you may know, there's some applications of ocean color remote sensing. One is for the marine food webs, implications for marine resources, and monitoring or investigating marine pollution and water qualities, and excuse me, ocean productivity and global carbon cycle, ocean acidification, marine biodiversity and function, and validation and improvement of Earth system ocean biogeochemical models, and data assimilation and assessing the marine ecosystem to climate changes. But these are for the global ocean, but also for the coastal and inland waters too. Here's about some differences in coastal inland waters with the remote sensing. Coastal and inland waters are optically complex, where non-phytoplankton components such as suspended sediment and colored dissolved organic matters, called the CDOM, are dominant due to mainly river runoffs and shallow bathymetry and tidal mixing. So it is highly required to have regionally tuned ocean color algorithms for more accurate observations in the coastal waters and inland waters, especially turbid waters. In addition, higher resolution satellite data can help to investigate the finer structures in the coastal environments. In general, polar orbit ocean color sensors has about 1 kilometer spatial resolution, but coastal region is a smaller area and more dynamic, so we need to higher resolution satellite data, such as Landsat A, about 30 meter spatial resolution, and I think it's Sentinel MSI, and there's a very high resolution CubeSat data. It's planet scope about 3 meter, but it's commercial sensor. Yeah, here's examples. As mentioned, global ocean color algorithms are not working very well in the coastal, turbid coastal waters. So here is one example of a water diffuser attenuation coefficient at 490 nanometer, which is called KD490. Some people may not familiar with this parameter. You can see that is water clarity or turbidity. There are some examples. A comparison matchup between model-derived KD490 and in situ KD490. The model KD490 derived using the standard models for the global ocean. So you can see those model-derived values is quite underestimated. This one is new inverse semi-analytical KD model for the turbid waters. That is basically for the Chesapeake Bay in the U.S. East Coast, but we also tested for other global coastal waters. So as you can see in the bottom left, bottom images, it's a modis derived KD490 images. The left one is using original algorithm. The right one is a new algorithm. You can see the original KD490 values is quite underestimated compared with the new algorithm derived KD490. And the right side is KD490 images in the Amazon River. You can see left and right the KD490 values images with the new algorithm looks more realistic. This one is water KD PA. PA is a photosynthetically available radiation. So you can see there is a visible band from about 400 to 700 nanometers. So there's a conversion algorithm. You can see here is KD pi from KD490. There's one is from clear ocean, but we also derived for the turbid the coastal waters. So we merged those two algorithms for the global oceans. There's various images, sample images in the bottom. Maybe many of people are interested in suspended sediment in the coastal waters. There is one of the examples from my previous research. These are MODIS climatology monthly suspended sediment using the regional algorithms. This is Siswanto et al. 2005, I think, for the Yellow Sea and East China Sea. So this map shows the seasonal, temporal, and spatial variations of total suspended sediment in the study area. You can see along the coastal area, the TSS is quite high in summertime. In the middle of the, in general, TSS decreased, and especially in the middle of the Yellow Sea, you can see there's reduced TSS values. Of course, outside of the bottom, the south and eastern area, there is a crucial current affected area, so TSS is quite low. And right plots are the seasonal changes in TSS for different area for the Bohai Sea and Yangtze River mouths, and bottom two is the coastal region. As you can see, TSS is quite high during the winter time. I think that is because of strong vertical mixing. And summertime is lower because of stratification. And the bottom right plot is an annual variation for about 10 years based on MODIS derived monthly TSS. There is annual variations. This is the diurnal changes of TSS in the west coast of Korean Peninsula. That is from Goshi sensor. So Goshi has the 8 measurement around the Korean Peninsula, Korean seas. So as you can see, a set of Goshi image provide hourly changes in hourly snapshot of TSS. The right figure is we select the two coastal region in the Korean Peninsula, the west coast of Korea, with the tidal current with the TSS values from the Goshi. So you can see Goshi derived the TSS has a strong correlation with the tidal mixing. Here's another example of TSS, suspended sediment, in the Chesapeake Bay, U.S. East Coast. There are several regional algorithms of TSS in the Chesapeake Bay. So one is based on KD490. TSS in Chesapeake Bay is quite a strong correlation with the KD490. So we derived these equations based on 15,000 in situ measurement and satellite data. So right top images from MODIS derived the seasonal climatology TSS images. You can see the spatial and temporal variations. And the bottom right is the monthly mean MODIS TSS to see the intennual variation in the three different bays. So as you can see, there are strong intennual variations which are related to river runoffs and the rains and storms. This one is quite a while ago. We tried to see the decadal changes from CWIPs and CGCS. So the left image is a ratio of CWIPs to CGCS long-term means, 443, NW 555, and chlorophyll A. You can see there's decreases in 443 and the increase in 555 and chlorophyll A. We also compare with the in situ data. The right side, there's a it's about 20 to 30 years time series of temperature, salinity, Secchi depth, and zooplankton biomass. You can see there is increasing or decreasing trend. So we can see we can use satellite data, ocean color satellite data. Now we have over 20 years satellite data, which can be used as the climate data record for the CDR. Here's the prime production models in the coastal regions. This one is we used the vertically resolved the prime production model by Trefrath and Shubhasan-Kedranas in 1988. There's the equation for the prime production algorithm, and we applied this algorithm with some modification or updating, tuning the parameters. So for the Yellow Sea, there's some example for you to calculate the light with the depths. We used KD490, but KD490 didn't work very well. So we used good relationship, strong relationship between Secchi depths and NFW 555. Also, we tuned some parameters, PB max and alpha B for this study area based on in situ measurement. Here are CWIPs derived prime production, daily prime production within the watercolor using the improved, the modified prime production models. You can see there's differences in May and September prime production in the Yellow Sea. There's another prime production study in the Chesapeake Bay. Actually, there is the paper for the Chesapeake Bay program, Chesapeake Bay production model. It's called the CBPM by Larry Harding, end of 1990s. I don't remember the year. This algorithm is based on VGPM. I tried to implement this algorithm for the satellite-derived MPP in the Chesapeake Bay, but it's quite complicated or not easy to use for satellite data. Also, there are some errors. So, using more updated in situ measurement, we improved this algorithm. Especially use the new derived KD490 algorithm, which can reduce the uncertainties in the coastal area, and it's about 2 to 3 times. And the PB-op, PB-max, that is derived from many different parameters in the original paper. We simplified that relationship, PB-opt, based on temperature, which worked better. So right side, there is a monthly MPP from Modis Aqua. You can see the seasonal patterns, and also they're spatially different, especially in the northern Chesapeake Bay. I mean upper bay, northern upper bay. In general, the prime production is lower. That is because of the light availability. And the summertime usually is a higher prime production. In the bottom plot is annual mean prime production from Modis Aqua in 2002 to 2011. Is a different base and whole bay, entire bay. You can see there's increasing trend, which would be related to nutrient input in the Chesapeake Bay. Now I want to show some human induced environmental changes using ocean color satellite data. There is a reclamation in the west coast of South Korea. It's called the Saemangum. There's a big dikes. You can see there's 2 dikes in the area, which was completed in April 2006. We wanted to see what happened before and after the dike completion. So left one is 2003, 1 year before dike completion. Right side is 2008 in summertime. That is a Modis derived NLW 645 normalized water raving radiance at 645 nanometer, which can be used index of suspended sediment. So as you can see, there's big changes. You can say suspended sediment decreased significantly after the dike completion, especially inside of the dike. Right side, this plot is monthly time series of Modis Aqua and BS SMPP derived SST, so sea surface temperature, and chlorophyll and suspended sediment inside of dike. As you can see, the red line is April 2006, the time of the dike completion. So there's a big changes, especially in the bottom TSS. It significantly decreased the TSS. The chlorophyll is increasing, but SST is similar. This significant decrease of TSS is related to tidal mixing. So after dike completion, tidal mixing reduced significantly. Then suspended sediment concentration is decreased too. Here's another example. It's an ocean dumping site in the Yellow Sea. Now is a stop, but before there was a dump site in the middle of the Yellow Sea. So that is a snapshot of Goshi derived KD490 from 9 o'clock in the morning to 4 p.m. In local time. Maybe you can see the red line from 10 a.m. and 11 to 4 p.m. You can see the red line. That is the track of the vessels, which is putting the organic matters into the water. But now it's stopped. But you can see that the changes. I like to show some diurnal changes in from the Goshi data in the Yangtze River mouth. You can see there's changes. You may not see clearly. I will show the animation in the next slide. In the bottom is diurnal changes in chlorophyll A and KD490 and NRW values. You can see there is the hourly changes from morning to evening, morning to late afternoon. Yeah, here is the animation from previous slide. Let me see it again. You can see there is diurnal changes which is related to tidal mixing and river runoffs. Next one is same day, same time, but KD490 algorithm. That is based on the new KD490 algorithm for the turbid coastal waters, which I already showed in previous slide. So there's strong, clear structures and changes. Yeah, here's animation. If I should make a better one. Yeah, you can see there's big changes. Even in the lake Taihu, you can see the changes from the Goshi images. Next one is one of my current research about hurricane impacts on water quality in the coastal waters. There's sample images. The left one is a Hurricane Ian last year, 2022. I don't know, some of you already heard about it. It's a very strong hurricane last year, September. It's early October. That is the Category 4 hurricane. So there's big damages in the Florida coastal region. There's these fierce SMPP images, 7-day composite images before hurricane and after hurricane. The upper image is SST, the bottom KD490. The red circle with the black line is the track of Hurricane Ian. Excuse me. So as you can see, there is a significantly decreased SST after hurricane, and KD490 values significantly increased along the coastal regions. Actually, I didn't add the high spatial resolution satellite images. Actually, I also checked the planet-scope images in the very coastal region. There is well, I shouldn't say, but very beautiful pictures of suspended sediment and sea domes in that area. Right side, there's I think it is a MODIS aqua images for the Hurricane Ivan in 2004 past Chesapeake Bay. The left one is 7 days composite image before and after Hurricane Ivan. SST, right side is chlorophyll A. similar to Hurricane Ian. Excuse me. There's a significantly decreased SST after hurricane, and right there is chlorophyll A. And the right bottom figure is a time series of chlorophyll A, actually fluorescence chlorophyll A, and turbidity measured from NOAA buoy in in the middle of the Chesapeake Bay, very coastal region. It's a stingray point in Chesapeake Bay. So you can see, for example, in turbidity, the red line is a hurricane passing day. So after hurricane, the turbidity significantly increased. So it goes about 10 days or 7 days after it's turning to normal. Excuse me. I think Gemma presented her research result about COVID lockdown effect in the Indian coastal region. Actually, I also, we had my colleagues in Korea, and I did a similar research for the Yellow Sea. Actually, this is impact on spring phytoplankton bloom in the middle of the Yellow Sea. Actually, in the Yellow Sea, this area strongly influenced by yellow dust and micro dust, actually from the east coast of China. There's a lot of industries. So after knockdown, it's all stopped. Then the pollutant nitrogen input is significantly reduced. Then phytoplankton size decreased in the area. There's the plot comparison between chlorophyll A in 2020 and mean chlorophyll A between 2015 and 19. So I think it is interesting to check after the lockdown finishes. Excuse me. There's this one is the water quality in inland waters. For example, I'm going to show the result in the Great Lakes in the USA, chlorophyll A and turbidity and seki depths. This is a regional turbidity algorithm in the Great Lakes. The top left plot is comparison between in situ turbidity measurement and Beer's derived KD490. We tried many different things, but there is a strongest relationship between turbidity and KD490, and we derived a very simple empirical algorithm, and it works reasonably well in the 5 Great Lakes area. Using the regional algorithms, we derived the Beer's turbidity images from 2012 to 2018. There's this monthly climatologic images of turbidity in the whole Great Lakes. You can see there is the differences, especially in the Lake Erie, the red part, small one. There's very shallow bathymetry. It's a picture. The water property is quite different from the other 4 Great Lakes. Next one is a chlorophyll A algorithm for the Great Lakes. There are some papers. The NASA standard OC3B algorithm is not working well in Great Lakes. There's a systematic scientifically biased. Then there are several regional algorithms for the Great Lakes. But all algorithms are based on different data set and approaches different. So we tested using more in situ measurement, but we found the standard algorithm is biased. Also, there are some issues in the regional algorithms for chlorophyll in the Great Lakes. So we tuned to derive the better the OC algorithms. There's equations, and we tested it works quite well in the Great Lakes, and generated the BLS SMPP chlorophyll images. Just one example, as you can see, the winter time, the chlorophyll concentration is quite low. The spring and summertime is higher. Especially, you can see the very high chlorophyll concentrations in Lake Erie. The red one. Especially summertime, August and September, chlorophyll concentration is very high. That's because of cyanobacteria bloom. Because annually, every year, there is a strong cyanobacteria bloom in the summertime in Lake Erie. There's another water quality parameters, the Secchi depth. There was Secchi depth algorithms based on NLW or RRS 551 or 550 nanometer. So we also tested and input data a little bit different. We had improved the Secchi depth algorithm here. It's also simple empirical algorithms. And we generated Secchi depth images from the BS SMPP. The pattern is similar to turbidity. The very shallow Secchi depths in the Lake Erie, especially winter time. I think that is because of the vertical mixing. And Lake Superior, so you can see in December, there's no buried pixels. That's because of the severe weather, like the very strong windstorm and ice covered in the area. There's another algorithm for the harmful algal bloom, the red tide. In Korean coastal area, every year there's a red tide. So this one is there's a very special event in 2013, I think. It's the east coast of South Korea peninsula, the southeastern area. There's a very significant red tide. We compared the images, the OC2C, this Gaussian images using standard Gaussian chlorophyll algorithm. You can see the pictures, but when you see the scale bar, the chlorophyll concentration is about 2 to 3, which is it's similar to just a normal condition in spring bloom. But in situ measurement, they show the chlorophyll concentrations is over 100, while the maximum is about 400, 500. So we improved the chlorophyll algorithm for the red tide based on 680 and 490 nanometer data. And the right side, you derive the chlorophyll image shows quite high concentrations, which is similar to in situ measurement. Also, there's diurnal changes from the Cauchy-derived chlorophyll using new algorithm. There is diurnal changes from morning to the afternoon. Usually, chlorophyll concentrations are higher in the afternoon. And the right side, we try to generate half warning index. So it can be used not forecasting, but near real-time forecasting or monitoring using satellite data. Here's one example of a phytoplankton size composition using CCI, OCCCI from 1998 to 2018 or sometime. This is not really coastal region, but including coastal region, that is Northern Bering Sea and Chukchi Sea. This image shows dominant phytoplankton size composition for three different phytoplankton size: phytoplankton, blue, nanoplankton in green, and red plankton. Red is a micro phytoplankton. So you can see in summertime, usually phytoplankton is dominant in the middle of the Bering Sea area. Next slide is about 20 years time series of the annual the dominant of the phytoplankton size composition, the annual mean in the summertime. The three different area, from north to south. One interesting is in the northern part, the SST is increasing trend, and microplankton is increasing, but both the phytoplankton and nanoplankton is decreasing. In the south part, the sea, you can see SST is increasing, but phytoplankton is increasing, but nano and microplankton is decreasing. So we can see the phytoplankton size composition is respond to the warming in that area. This is an example of a habitat suitability index for the fisheries in the Korean waters. This HSI index for the left one is Japanese common squid, right one is chook mackerel. This index is based on primary production from the ocean color satellite data to detect and forecast fishing ground information to understand the recent changes in fisheries resources. This one is it may not be related to coastal region, but that is chlorophyll A derived from NDVI in the tidal flat using Landsat 8 data. So there is a strong relationship between chlorophyll A and NDVI in the tidal flat. So there are some examples. We are going to try to estimate the time production in the tidal flat using this information. I mentioned in previous slide, we need to higher spatial resolution data in the coastal regions. These are some examples of high spatial resolution. The Landsat 8, the left one is a suspended particulate matter, the TSS, suspended sediment in the very coastal region. And the second one is one sample images from Seahawk, which is the first CubeSat. I think it's about 100-meter spatial resolutions. I'm going to show the information about that. And the right side, upper images of PlanetScope 3-meter images, or RGB, and suspended sediment. You can see there is a red spot in the upper images, which is the ocean wind farms in the Korean coastal region. And the bottom is SPM images. You can see the tailing from the wind farms. And right at the bottom is one of the example from PlanetScope 3-meter data, which is the seaweed aquaculture in the Korean coastal regions. In Korea coastal region, a lot of aquacultures, we can see the seaweeds from the very high spatial resolution satellite data. I showed some examples from my previous study, algorithms and applications in the coastal and inland waters. So I'm trying to show some future sensors and see the applications, what you can do with the future sensors. Maybe this table not updated well, but there are some scheduled satellite ocean color sensors. As you may know, the red OCI PACE sensor will be launched this year or next year, which is a 1 kilometer spatial resolution, but it has 186 bands from 350 to 2250. And there's another one, SBG, and Glimmer, and BS sensor. BS satellite will launch it continuously. And maybe other people also know about the sensors, future sensors from other countries. Here's different sensors for future compared with the traditional polar orbit ocean color sensors. The PACE, as mentioned, which is a hyperspectral radiometer from UV to near IR at about 5 nanometer resolutions. This sensor, this satellite will be launched this year or next year. And another one is SBG, surface biology and geology sensor, hyperspectral radiometer at 10 nanometer with a high spatial resolution, is about 30 meter. This sensor more focused on inland and coastal ecosystem, but I don't know if this sensor is approved or not. The NASA JPL, I think, and colleagues are working for this sensor. Another one is Glimmer. I think it's approved before pandemic, but I don't know when it will be launched. I think that is this one could be the first geostationary ocean color sensors in USA. It's about 15 times per day, and hyperspectral ocean color radiometry, but it covers US coast and Amazon River and focusing more on coastal ecosystems. The other one is GeoExo. NOAA also approved to launch geostationary ocean color sensors. NOAA already has more than 10 geostationary satellites or focus on the meteorology, it's a SST or temperature. But NOAA has a plan to launch geostationary ocean color sensors, but it will be about 2030s around to observe ocean productivity and ecosystem changes, coastal inland water quality, and coastal hazards. Here's a small size satellite. It's called CubeSat. I already showed I mentioned the Sea-Hope. That is first ocean color CubeSat launched in 2018 December. Very small weight is about less than 5 kilometer, and 18-day repeat orbit. It's about 120 spatial resolutions. The right bottom is the example of the Sea-Hope CubeSat images compared with the MODIS. But there are a lot more CubeSat images, but from commercial sectors, as I mentioned, the PlanetScope. Nano satellite or CubeSat, which is relatively very cheap compared with the polar orbit sensors, and a small size instrument and high spatial resolution. This is 100 for Sea-Hope, but commercial sensor has about 3 meter or 1 meter, so you have to pay a lot of money. And CubeSat can launch multiple satellites in the same time, which can read the coastal inland water observing paradigm. Okay, with the future sensors, what we can do, we can reduce uncertainties and improve or develop robust ocean color algorithms, especially in the coastal waters, such as phytoplankton pigment communities and coral reef functional diversity, etc. And productivity and carbon assessment in coastal marshes, tidal flat, and wetlands. And we can improve the detection of water quality, harmful algal bloom, microalgae bloom, and oil spill accidents to enhance the monitoring system, and quantify vertical transport of carbon, nutrients, and oxygen due to the diurnal vertical migration of phytoplankton aggregations. And we can use the satellite data for the fisheries aquaculture site selection tool, and advanced remote sensing of marine debris and microplastic, which could be very challenging. I think this is, yeah, I'm done. Please, if you have any question, let me know. We can discuss about it.